Hello, and thank you for watching my video. This is a follow-up and overview of quadratic polynomial number theorem, plus some news. And these slides were prepared for a talk I was supposed to give at Math Jams UK this year, but the talk didn't happen because of technical difficulties. So I thought I'd use them here to sort of go over what those videos on quadratic polynomial number theorem are all about, and point in a direction where you can learn more about what's going on. So quadratic polynomial number theorem is a generalization of Euler's pentagonal number theorem, where this product equals this sum when q is left unevaluated, giving the exponents that match the values of this quadratic, and we can designate that either by this formula or by a value representation where we're taking the value at f-1, f0, and f of 1 to uniquely determine the quadratic. Any three known values will uniquely determine it. So let's choose these three, and we'll find that that's a convenient way to designate this quadratic. Euler's pentagonal number theorem is important because of its relation to partitions, which are the number of ways of writing numbers less than or equal to n that sum to n. So for example, 4 can be the sum of 4 or 3 plus 1, etc. And we get that the number of partitions of n equals 4 is 5. And so the inverse of the generating function on the previous slide gives this Q series sequence where the exponents are now the index, and it's the coefficients that are of interest because they are the partition numbers. The P of n, 1, 1, 2, 3, 5, 7, and coefficients 1, 1, 2, 3, 5, 7. So quadratic polynomial number theorem generalizes Euler's pentagonal number theorem by substituting this quadratic for the standard quadratic, and then taking this over the parameters alpha beta, where alpha is less than beta, and both alpha and beta are elements of the natural numbers, meaning 0 is out of the picture at the moment, and so is alpha equals beta. We're not considering that at the moment. So alpha must be at least 1, beta must be at least 2. And then taking this, inserting it into Euler's pentagonal number theorem, and that creates the quadratic polynomial number theorem, and this induces a structure throughout the theory of partitions to give us natural definitions for these functions, a restricted partitions function such that it is counting the number of partitions of n with all parts equivalent to either alpha, beta, or 0 mod alpha plus beta. And similarly, using standard recurrences, we get that sigma alpha beta of n is summing the divisors of n that are equivalent to either alpha, beta, or 0 mod alpha plus beta. So the partition function is counting, the sigma function is summing, and if alpha equals 1 and beta equals 2, this corresponds to the minimum pair and the base case and the unrestricted partitions function, because every n must be equivalent to either 1, 2, or 0 mod 3. So it includes them all, and it doesn't overcount any of them, I should say. To see a lot more about this, including some Mathematica code and all kinds of things, check out the online Encyclopedia of Integer Sequences. OEIS entry number A347187 is the Sloan's entry that was published for the polynomial coefficients triangle, which I'll talk about here in a second. So let's take an example here. We'll keep alpha 1, but we'll go to beta equals 3. That's our quadratic, or in value representation, this 301. And what's nice about this kind of representation is that under this formalism here, the quadratic in question will always be beta 0 alpha. And in this case, it gives us the hexagonal numbers in the positive side, and we could call the negative side the generalized hexagonal numbers altogether, but altogether these numbers are the n choose 2 binomials for n greater than 0, and they also are known as the triangular numbers. And such is the case whenever alpha equals 1. You fix alpha equals 1. This isolates the quadratics of the g-gonal numbers. So the pentagonal numbers, when alpha equals 1, beta equals 2. Notice that g of g-gonal will always be beta plus 3. So here with 1, 3, we're getting the hexagonal numbers. If we did 1, 4, we would have the septagonal numbers, etc. Then, so that's the case for alpha equals 1. If you take alpha greater than 1, then all bets are off. All right, so with our quadratic thus and our set defined thus, we are looking at the natural numbers that are equivalent to 1, 3, or 0 mod 4. And that product form of the generating function can be broken up into terms consistent with their congruency class, I should say, and or by the summation form where everything's the same. We're just substituting in the alpha beta quadratic for the regular quadratic. And so in this case, similar to getting the pentagonal numbers as exponents in the 1, 2 case, here in the 1, 3 case, we're getting the hexagonal numbers as hexagonals, or the generalized hexagonals, aka the triangular numbers, aka the n choose 2 binomials, as expected. And here are the coefficients in this sequence, and we know if we invert that we should be getting what we do get, which is the sequence of partitions such that all parts are equivalent to either 1, 3, 0, 1, 3, or 0 mod 4. And that's just by inverting what we had before. This is just a way to verify it. Really, it's just long division, taking that coefficient sequence from before, and we're putting it as the denominator, and then just doing the long division. And you can see that's one way we can develop this sequence. Here is a sigma example. We'll take our k index and we'll circle every value of k that matches a value of the quadratic in question, here 1, 3, 6, 10, and take our sequence of the restricted partitions and then multiply it by the first one and add it starting in the first position. The second one, the value is 3, multiply it by the sequence of partitions and add it starting in the third position, etc. So by the time we get here, we're going to multiply this by 6 and we're going to subtract it from the rest. And similarly, we're going to do it for 10, subtracting for 10. So you can see where this is plus, plus, minus, minus, with the solutions of fk here as our coefficients. This is just following that standard Euler recurrence that gives sigma n in terms of partitions of k, where k are less than or equal to n. And it just applies across the alpha beta generalization. So when we add these up, we do indeed get these numbers here, which are given. Here are all of the divisors of the index numbers, and you can see we just circled all the 1s, circle all the 3s, but don't circle the 2s or the 6s or the 10s because they do not meet the modular criteria. Sum them up, and yes, we get the same numbers, and it's a really fascinating connection. Alrighty, this is a good place to stop, and I'll make a part 2 to cover the rest, which is basically this idea of more over partitions. In addition to partitions and then over partitions, the process repeats, and one can define this thing that we'll call more over partitions. Then we're going to take a closer look at the sigma recurrence and the resultant alpha beta generalized sigma function, and how it shows us that the sigma sum of divisors function I don't know how else to put it, but sigma has seasons like spring, summer, fall, winter. So check out the part 2 of this to see more about that. Thank you for watching my video. Please like and subscribe to my channel. And please check out the PayPal link where you can contribute to support my research. Thank you again.